Hello, welcome back. We have been talking about AC circuits, alternating current circuits. And we started by looking at an AC circuit that had a resistor. And then we looked at an AC circuit that had a capacitor. And now what we're going to do is we're going to look at AC circuits that have a resistor and a capacitor. So these will be RC circuits. And these RC circuits are special because we can use them to create low pass filters and high pass filters. So let's take a look at these RC AC circuits. So here we have an AC circuit. It's got an alternating current right here, where the EMF is equal to the peak EMF naught times cos omega t. And we have a resistor and a capacitor. So the figure here shows a circuit in which a resistor R and a capacitor C are in series with an EMF oscillating at an angular frequency omega. Now we remember that if we have a capacitor that is in an AC circuit, that we can define a capacitive reactance. And that capacitive reactance is equal to 1 over omega times C, the capacitance. So it is inversely related to the angular frequency. We also saw that once we defined that capacitive reactance, that we can then see how that is related to our peak current. And we saw that the peak current equals the peak voltage over the reactance. So if the frequency here is very low, so the frequency is low, that means that the capacitive reactance, this capacitive reactance, will be very large. And if the capacitive reactance right here is very large, that means that the peak current will be very small. Now, on the other hand, let's get rid of those and flip it. So now on the other hand, let's look and say if instead the frequency is very high, so now our frequency is very high, then in that case, the capacitive reactance will be very small. It will approach 0. And if that approaches 0, right here, the capacitive reactance approaches 0, then the peak current in that case will just be determined by the resistance alone. And so we know that when we have a peak current determined by resistance alone, that is just Ohm's law, ver. And so we can just say that in that case, delta V equals IR. And so in this case, our peak current will be IR equals our peak EMF over the resistance. So let's see if we can analyze these RC circuits by using our phasor diagrams that we just learned about. So here's our RC circuit again. Now we want to start by drawing a current of phasor length, capital I. So that's our peak current length, capital I. And we only have to do one current, of course, because these are in series. So our current is the same. So this is a starting point because the series circuit elements have the same current I. That's why we want to start with I. Everything has the same current I. And it doesn't really matter at which angle we draw the first phasor. So the first current phasor, it doesn't matter how we draw it, which angle we draw it at. Now, what's important is when we then want to draw in VR and VC. So first, the current and voltage of a resistor we know are in phase. So in that case, we want to draw our resistor voltage phasor of length VR. It's going to be parallel to the current phasor I because they are in phase. The capacitor voltage, however, is not in phase with the current. The capacitor current leads the capacitor voltage by 90 degrees. So we want to draw the capacitor voltage 90 degrees. No, we want to draw it 90 degrees behind the current phasor. Now that we have those two voltages, we are just going to say that the series resistor and capacitor, we know that they are in parallel by looking right here. They are in parallel with the EMF. So their instantaneous voltages must satisfy VR, that's instantaneous, plus VC, an instantaneous voltage, must equal the EMF. This is a vector addition of phasors. So we're going to be adding together the vector addition of phasors here. And so we see that, that the vectors of the instantaneous VR right here and the instantaneous VC will equal the EMF. And the EMF is EMF naught cos omega t. So when we draw EMF naught, that angle must be omega t. Now the length of the EMF phasor, EMF naught, is going to be the hypotenuse of a right triangle formed by the resistor and capacitor phasors. And since it is the hypotenuse, we can just use Pythagorean's theorem to find the length of that hypotenuse. A squared plus B squared equals C squared. So now we see that the relationship we have is that EMF naught squared equals VR squared plus VC squared. And that's based just on peak values. Those are the peak values. Those are not the instantaneous values. So those are the peak values that are going to give us the relationship between the peak EMF and the peak resistor voltage and the peak capacitor voltage. Now the peak voltages can then be related to the peak current as well. The resistor voltage, of course, is related by Ver, and to the capacitor voltage, as we just saw, we can relate that to the current by, as the current times the capacitive reactance. So in this case, let's go ahead and rewrite this equation right here. We have EMF naught squared equals VR squared plus VC squared. And now I'm going to substitute in for VC, I XC, and for VR, IR. So rewriting that, I have IR squared plus IXC squared. I'm going to go ahead and multiply. I'm going to go ahead and put through my, distribute my squareds here. I squared R squared plus I squared XC squared. And now that I've put that through, I can go ahead and factor out my I squared. And so I'm going to have this be R squared plus XC squared times the factored out I squared. Now we also can remember that we just defined our reactive capacitance, and that is equal to 1 over omega times the capacitance. So putting this in for my capacitive reactance, I get R squared plus 1 over omega squared C squared. All of that times I squared. Now, this is EMF naught in terms of I, but we also can solve for the peak current. So we're going to go backwards. So I'm going to take my EMF naught squared equals R squared plus 1 over omega squared C squared times I squared. And now I'm just going to solve for the peak current. So I'm going to divide both sides by R squared plus 1 over omega squared C squared. And that term on this side will cancel. And then I need to square both sides. And so I see that I peak current will be equal to my peak EMF over the square root of R squared plus 1 over omega squared C squared. So then I can go ahead and find the two peak voltages, because I know that the peak voltage, the peak resistor voltage is equal to VER, and I know that the peak capacitor voltage is equal to the peak current times the reactance. So if I have VER here and I put in what I have for my peak current here, I have now it doesn't look like a very good EMF, my EMF naught, here we go, EMF naught times R over the square root of R squared plus 1 over omega squared C squared, which is much better written there. And now for my capacitor voltage, my peak capacitor voltage, that's I times my reactance. That will be my EMF naught times my reactance over the square root of R squared plus 1 over omega squared C squared. And I remember that my reactance is equal to 1 over omega times C. And so this I can then rewrite as EMF naught over omega times C over the square root of R squared plus 1 over omega squared C squared. Now these may look a little complicated, but in what we notice is that what we want to think about is what happens as omega gets really, really big. So if omega goes to infinity, this term right here is going to go to 0. So this right here, as omega goes to infinity, what we see is that in this case, we then have, so this becomes EMF naught times R over the square root of R squared. And so these will just cancel. And so this just equals EMF naught. Down here, however, as omega goes to infinity, this whole term will go to 0. And so this tends to, and so to the capacitor voltage tends to 0. However, there is a moment when these two are equal. And so setting these two equations equal to each other, we'll find a moment when they are equal. So then once we've done that, we can plot this out. So this figure, it shows a graph of the resistor and capacitor peak voltages. That's the VC and the VR that we were just looking at, as functions of the EMF angular frequency omega. And so what we just saw was that as omega increases, as it gets a lot bigger, the capacitor voltage right here approaches 0. So this one approaches 0. Whereas the resistor voltage right here starts out as 0. And as omega approaches infinity, the resistor voltage approaches EMF naught. Now there is a moment where they cross. That is right here. And the frequency at which VR equals VC is called the crossover frequency. It is written omega C. And it is equal to 1 over RC. And this frequency is important because when we have these circuits, we can design them in such a way that that frequency will be our limiting frequency. So let's see how we can do that. So in this figure, we have an RC circuit in which the output voltage, the way we have this set up right here, our output voltage is going to be equal to VC. It's going to be the voltage across the capacitor. So if it's equal to VC, In that case, since VC goes to 0 as we go to, as omega goes to infinity, this will only transmit frequencies that are less than the crossover frequency, and it will block all frequencies that are greater than the crossover frequency. This circuit is called a low pass filter. It only allows the lower frequencies to pass. Now, what happens if we flip the position of the resistor and the capacitor? So here we have, in this case, we have the capacitor first in our circuit, and we have the resistor over here. And in this case, our output voltage that we're reading is going to be the resistor voltage. Well, the resistor voltage, well then, if that's the output voltage, that will transmit frequencies that are greater than the crossover frequency, and it will block the frequencies that are less than the crossover frequency. This circuit is called a high pass filter. So what we have seen is that RC circuits are even more useful when we use AC, because what we can do when we have an AC circuit that has both a resistor and a capacitor is we can create a low pass filter or a high pass filter.